Well, this is the second part of what if analysis on chapter 5. Okay, these are the subtopics. I already gave you the part 1, but I'll give you a review of what has been taken up in part 1. For our review, what if analysis involves addressing some questions about what would happen to the optimal solution if different assumptions were made about future conditions. So what are these changes? Usually it's about changes in costs, prices, market conditions, and also they stem from inaccuracies or errors from the data that has been gathered within the organization. Um, Sensitivity analysis involves checking how sensitive the optimal solution is to the value of each parameter. And sensitivity analysis is a vital part of what-if analysis. Sensitivity analysis performs the following. It pinpoints the sensitive parameters and are considered sensitive if even a small change in its value changes the optimal solution. Moreover, it indicates whether a resulting change in a parameter of the model changes the optimal solution. Lastly, it provides valuable guidance to management regarding the impact of altering these policy decisions. The procedure in our sensitivity analysis are the following. First, you need to identify the parameters. And these parameters are found in the coefficients in the objective function. And they're also found in the right-hand sides of the functional constraints. In our previous discussions, I showed you the spreadsheet and also the location of these parameters. So we have, I presented two kinds of parameters, those in the coefficients. Specifically, they were the numerical coefficients pertaining to the unit profit. And the other parameters were in the right-hand sides of the functional constraints. They are located in the middle part of the spreadsheet, and these functional constraints are in terms of the hours available. So they are located in the right side of the inequality signs. Then you use a spreadsheet formulation of the model with already its optimal solution on Excel. And on the spreadsheet, just change one of the parameters, then run Analytic Solver. Okay, now you need to record the changes in the optimal solution. So every time you change one parameter, you need to record the corresponding optimal solution. So you're going to have many trials, and each time you try, you have to record. You can do this manually, and you can also do it using Excel. And in both cases, you have to generate the parameter analysis report. Okay, then when changing this parameter, it does not change the optimal solution. Therefore, we would say that the parameter is not sensitive. Otherwise, sensitive, which means to say that even if a small change in the parameter would change the optimal solution, then we would say that that parameter is sensitive. Oh, that's it, no? The important thing is for you to identify the parameters, and then you're going to change one parameter at a time, and then you need to record the whatever the optimal solution is. Okay, so that was part one, changing the objective coefficients. Wherein you can change one coefficient at a time, or you can change two coefficients simultaneously. Okay, and I also tried to explain, no, how to interpret a parameter analysis report. And the parameter analysis report is further summarized into a sensitivity report. Okay, so I have already explained this, no? These two kinds of report. The simultaneous changes in the objective coefficients involve testing whether these simultaneous changes will change the optimal solution. Because management would want to know if there is a guarantee, no, if the optimal solution is guaranteed to remain unchanged. Okay, so this involves applying changes in the objective coefficients, then run solver. Then generate the two-way parameter analysis report. And then you will use the 100% rule if there are two simultaneous changes on the objective coefficients. And then evaluate the sum of the percentage changes. Then use the 100% rule. If the sum of the percentage changes is less than or equal to 100%, there is a guarantee that the original optimal solution is still optimal. And beyond 100% would tell us that we are not sure whether the original optimal solution is still optimal or still valid. Now, part two, which is our topic today, involves changing the functional constraints. The functional constraints are found as coefficients on the left-hand sides of the constraints or in the right-hand sides. But our focus today is changing the functional constraints on the right-hand sides. Let us be reminded first that the changing of the right-hand side values is due to certain managerial policy decisions changes as well, no, on these policies. And to analyze the effect of altering such decisions and if they can still be improved. So changing any of the right-hand side values, the objective of this is to see if there could still be, if it's possible to improve, especially the performance level, no, like the total profit, no. If the total profit, for example, could still be improved after, let's say, adding a little or some or a few hours, adding a few hours to the operating hours. Let's say adding an hour to one of the plants of the firm. Now, the procedure involves step one is to change one of the right-hand side and then run solver. So this is quite similar to part one, like changing one of the coefficients, then run solver. So in this case, it's the same procedure. except that the thing involved is the right-hand side or one of the right-hand side numbers. Then run solver. And you do this repeatedly for different values. Then afterward, you will generate the parameter analysis report. So what I'm giving you actually is a summary of what we will find in this topic. And then there's also a sensitivity report, which will show the allowable range of values for which the constraint's shadow price remains valid. And now the shadow price for a functional constraint is the rate at which the value of the objective function can be increased by increasing the right-hand side of the constraint even by a small amount, such that the change in profit is equal to the proposed increase in the right-hand side constant times the shadow price. More on this, no? This will be explained in detail. Okay. So here, there are three spreadsheets. No, you're looking at three spreadsheets. The first on the left side, the upper part, focus on the hours available because we're talking now about the constraints. So we will focus our our mind, no? We will look at the functional part, no, the functional constraints of the spreadsheet, and they are found in the middle. So there you have hours used and hours available. We will focus on the hours available, wherein you have plant 1, 4 hours, plant 2, 13 hours, and plant 3, 18 hours. Look at the total profit as well. We will look at the effect on the total profit as one of the right-hand side values, as we change one of these hours available. Okay, so let's look at plan 2. Um, it used to be 12 hours. Now it's been increased to 13 hours. And the total profit increases by $150 per week. So the original total profit, when it was 12 hours in Plant 2, it was 3,600. Increasing Plant 2 with 1 hour gives an additional profit of $150 per week. Now let's look at the right side spreadsheet. The hours available in Plan 2 have been further increased from 13 to 18 hours. Now look at the total profit. It increases by $750 per week, or 150 per hour added for Plan 2. Then let's look at the last spreadsheet below. So what change do you notice? Again, in Plan 2, the hours available were changed or increased from 18 to 20. Now look at the total profit. Is there any change? There is no change at all. So there is no use adding more hours to Plan 2. There's no use adding 2 more hours to Plan 2 because it did not change the total profit. It did not increase the total profit. So here we have the parameter analysis report for the hours available in Plan 2. And it's that is specific number of hours that were being changed. So on column A, we see the different hours available in Plan 2. Let's look at the number. Okay, the Plan 2's original hours were 12, no, on the spreadsheet. And these are the different scenarios in terms of total profit. So we will focus our attention on column D, which is the total profit. The effect on total profit. Let's look at the effect on total profit as the hours available in Plant 2 were being changed. We see that the lowest hours, the what used to be 12 hours, uh, was being decreased, no? From 10 to 11 to 10 up to 4 hours only. And see, we saw the effect, no, on the total profit at the right. I mean on column D. We also being presented here the the scenario on the total profit as the hours available in Plant 2 was increased from 12 to 13, 14, and so on, and up to 20 hours. So look at the effect on the total profit on column D. And then there is the incremental profit presented on column E. You will notice the incremental profit is constant, no, within a specific range. So we have uh, $150, which remains the same within the range of what? Within uh, after 6 hours. After 6 hours until it was 150 until the 18th hour. Okay, so we have, and we call this constant value of 150 hours, the incremental profit. We call it the shadow price. And that shadow price, a specific range, it's being shown here to be within 6. It's the shadow price, no, has this range of greater than or equal to 6 hours, um and less than or equal to 18. So this is the range of the shadow price. So it's really the shadow price which is the concern of changing the right hand side value or values. Aside from the parameter analysis report, we also have the sensitivity report. Um, the upper part has been discussed in part 1. So our concern now is the lower part of the table, which is relevant to our discussion of the right-hand side. So here we have plant 1, plant 2, plant 3, hours used. Okay, so we'll focus on the shadow price and the allowable increase and allowable decrease in terms of hours. So we have 4, 12, and 18 hours, which are on the right-hand side constraint of the functional constraint. Okay, so our table here shows that plant 1, okay, plant 1's 4 hours can be increased infinitely, okay, and it can be decreased by 2 hours only to maintain the shadow price at 0. Similarly, for the constraint of 12, the allowable increase in hours is 6, and the allowable decrease is 6 as well. So that's the range, which means to say that if we add 6 hours to 12, without touching the other parameters, we can maintain the shadow price at 150. So beyond this allowable increase, let's say 7, instead of 6, it's 7. So if we add 7 to 12, that becomes 19. So if we change this to 19, the shadow price of 150 will no longer be valid. It's no longer applicable. Okay, and then allowable decrease is 6 hours, which means that if we deduct 6 from 12, so we have 6 here, we can still maintain the shadow price of 150. Okay, so beyond this allowable decrease, let's say 7 or 8, so we will have 12 minus 7, that will be 5. If that's the case, the shadow price of 150 will no longer be valid. It's the same explanation for, for constraint 18. The shadow price of 100 will remain valid only within this range of allowable increase and allowable decrease. Well, the shadow price is important because it tells us about the additional profit that or the additional profit that or the incremental profit that can be maintained within this range of allowable increase and decrease. Okay, some notes. The managerial policy decisions involving right-hand sides are interrelated. So changes in this decision should be considered simultaneously. So if we change in plan 2, no, if we have uh, in our on our spreadsheet, if we have, though, let's look at the, okay, on the spreadsheet. Um, we have plant 1, 18 hours, and we have on plant 3, 18 hours. But our original values were actually 12 and 18. Um, in reality, we cannot keep increasing the hours in plant 2, but usually for practical purposes, we cannot increase the hours in plant 2 without changing the hours in plant 3, which makes the hours um, in both plants variable and they are connected, which means that we can transfer, usually the practice is to transfer hours available from plant 2 to plant 3 or from plant 3 to plant 2. So it's just the two are connected. No? The two plants are connected. Therefore, the two right-hand sides are connected as well, such that a policy is bound to affect both the hours available in both plants. Therefore, we could use a two-way parameter analysis report to investigate how the profit and optimal production rates would vary or different combinations of the number of hours available in plant 2 and plant 3. It is also highlighted that we're more interested on those combinations of hours on plant 2 and plant 3, which involves shifting of available hours between these two plants. And for this analysis, we could, a one-way parameter analysis is sufficient. Okay, so we don't need a two-way parameter analysis report that involves two plants because we are simply shifting hours from one plant to the other. Okay, so here we are being shown simultaneous changes in right-hand side. So it is incidental, no, that when we change 1 hour in an hour, we change the hours, no, in one plant, it is incidental that the number of hours in the other plant will also change. Therefore, simultaneous changes in the right-hand side is inevitable. Okay, so let's look at, here we have two spreadsheets. Let's look at the left side first. One available hour in plant 3, okay, has been shifted to plant 2. So, what used to be 17 hours, what used to be 18, 18 hours in plant 3 is now 17 hours because the 18th hour was transferred to plant 2. Okay. And the total profit increases by $50 per week. So what used to be $3,600 is now has increased to $3,650. So that's the effect of shifting 1 hour from plant 3 to plant 2. Now let's look at the other spreadsheet. Okay, so what's being shown here? We have the original hours available of 4, 12, and 18 before the change. Okay, so we have 3,600 here. So we are also being shown, no, on column H, the total hours for the combined two plants, plant 2 and plant 3. Okay, so it fixes, no, the total hours to 30 hours such that the sum of so moving, no, which it constrains actually that the hours shifted from 12 to 18, or from 18 to, I mean, from plant 1 to plant 2, or from plant 2 to plant 3, should maintain the sum at 30 hours. And that is done by inserting a formula into cell G8 that keeps the total number of hours available in plant 2 and plant 3 equal to 30. It will be possible then to generate a one-way parameter analysis report that shows the effect of shifting more and more of the hours from plant 3 to plant 2, and that is being shown below. So we have columns A and B, which show the transfer of hours, okay, within the two plants. We have 12 plus 18, 13. Then 1 hour transferred from plant 3 to plant 2, which makes it 13 and 17 combination. Then we have 14 and 16 combinations. And then we have 15 and 15 combination, and so on. Now let's look at column E, the total profit column. And then let's look also at the incremental profit. So we see increases in total profit, but then at some point, there is already a decrease in the total profit, and that increases and decreases are being shown on column F for the incremental profit. And you see here that it's already negative. It started turning negative when we have the combination of 16 hours in plant 2 and 14 hours in plant 3, which implies or tells us, no, that there is a limit to transferring the hours from plant 3 to plant 2. Okay. So it's really very important to calculate for the incremental profit resulting from the change in the simultaneous changes in the right-hand side. Okay. Now, if there are simultaneous changes in the right-hand side values, we will also use the 100% rule. So how do you do this? We simply compute for the percentage changes in each of the right-hand side, okay? And then divide it by the allowable increase and the other one by the allowable. The other one is the divisor for one is the allowable increase, and the divisor for the other one is the allowable decrease. And then sum up the percentage changes and then evaluate. Evaluate using the 100% rule, such that if the sum of the percentage changes does not exceed 100%, the shadow prices, no, not the optimal solution. Okay, the shadow prices definitely will still be valid. And if the sum does exceed 100%, then we cannot be sure. Okay, so for the divisor of the percentage changes, we will go back to the sensitivity report that shows the allowable range. So the aspect, no, the important aspect that is related to the changes in the right-hand side, functional constraints, is actually the shadow price. The shadow price tells us the incremental um, increase, or I mean the incremental is the increase in the profit, which will remain valid within a specific range of changes in the right-hand side. Okay. The 100% rule for simultaneous changes, okay, in the right-hand side of the functional constraints involves changing the value of some right-hand side as long as changes are not too large. Because if we do, as you had seen, no, earlier, it is possible that the incremental profit would turn negative. The procedure is to calculate the percentage changes in the allowable range and sum up these percentages, and then find out if the changes are small enough. There you have, again, the 100% rule. If the sum of the percentage changes do not exceed 100%, then the shadow prices remain valid. Okay, so the shadow price tells us, and this is actually the value which refers to the incremental profit that remains valid within a range of changes in the right-hand side constraints. Okay, now we have robust optimization, last topic, subtopic actually. Well, actually, robust optimization is another, I would say, contingency, because what if analysis is a contingency? And so with sensitivity analysis, it's a contingency. Now we have the last contingency plan, which is about robust optimization. Um, what do we mean by this? In every managerial or in every management policy, of course, there are consequences. And we build sensitivity analysis to prepare for um, some gaps, or to prepare for things we're not sure about. no? For any possibilities, we prepare and we call it what if, no? We do a what if analysis or sensitivity analysis to make sure or to uh, it is an effort to guarantee that we will succeed, no? Or that, for example, that we will profit or we will be able to maintain a particular profit level. So we do a sensitivity analysis so that or to test, no, if the optimal solution is guaranteed or some changes that may occur, to so we allow in sensitivity analysis, we try to guarantee, no, or come up with some amount of certainty if the solution that we have will still be valid, within a particular um, amount of changes. Okay. But maybe that could not be enough. No, it may not be enough that we resort to another way to guarantee or to further guarantee success in our in our, let's say, production. If we are into production, we want to see that we will be able to guarantee that we have a uh, a contingency or a solution, okay, to to uh, in order to ensure, no, or at least to some extent, ensure our success, or at least minimize the failure. Yan. So, kumbaga, yung sensitivity analysis is used to guarantee if we have a solution that is um, really a solution. But then there is no 100%. We cannot be 100% sure about the assurance. No, we cannot be 100% sure that that it's fail proof. No? Therefore, management, no, still try to come up with another way or another strategy to really guarantee a or to make sure that we will not have any problem at all, or we'll be able to minimize the problems, no, that may occur specifically on our spreadsheet model, specifically, no, about our constraints. Now, the robust optimization here is better applied to the functional constraints. Okay. Now let's look at this. The purpose of recall that the purpose of sensitivity analysis is to pinpoint the sensitive parameters such that a small change in their value changes the optimal solution, and for which caution be taken in order to prevent erroneous optimal solution. But then serious estimation errors may still possibly occur, thus rendering the optimal solution not optimal at all. Therefore, we have robust optimization to address this problem. Okay, robust optimization uh, has the following justifications. First, it is not possible to estimate parameters with as much accuracy as desired. And the seriousness of the consequences depends somewhat on whether there is any latitude in the functional constraint. The latitude we're talking about here is the allowance within which to move. Yan, parang halimbawa, 'di ba, yung uh, when we are given, no, let's say client would give us a project and we inform him about our lead time. So instead of telling him about the exact time that we would need to produce his order, instead of instead of telling him that we need 7 days, you would tell him that you need 10 days. And that gives you latitude, gives you an allowance, so that you're also avoiding his frustration, that if you're only given 7 days, then that may be too tight, no? So you don't have any allowance at all. You have no tawag mo dyan, latitude, no? Or pasobra in Tagalog. So because, changes would happen, there could be emergencies, or there could be um, the inability as well, no, of your suppliers to give you your required supplies or materials, no, which you need in or for your project, which you will need for your project. So that's the latitude where an example of a latitude we're talking about here. Now, a soft constraint is a constraint that can be violated a little bit without serious complications. Um, what is this about? So I'll give you an example. Let's say in baking, no, in baking, what's this? When we bake, let's say, we bake a pandesal, pandesal, a type of bread. Okay. So we have the constraints, the resource constraints or the material constraints in baking pandesal. Okay, so which of these resources or raw materials is a soft constraint in baking pandesal? So what are the materials we use here? We use flour, yeast, sugar, and milk. Okay. Now the milk, I would say, is a soft constraint, and sugar as well is a soft constraint. Why? Because we don't need a lot of milk to place on our pandesal to make it a pandesal, look like pandesal. Bake it as a pandesal, no, as the final product. So that's a soft constraint. It can be violated a little bit. You can add a little more, or you can lessen the milk a little more. And still, you can bake it. The output will still be a pandesal. Will look like a pandesal, taste like a pandesal. Okay. Now, a hard constraint, on the other hand, is a constraint that must be satisfied. So what is that hard constraint on a pandesal? It is the yeast. If you put too much yeast, no, in baking a pandesal, it does not become a pandesal. It will uh, it will have more air in it, no, because it will ferment a lot. No? It might become, and if you added more milk into it, no, plus a lot of yeast, and still you added baking powder, then it might look like a sponge cake already, or some other kind of bread, no longer a pandesal. So that's a hard constraint. So it's about uh, the materials, no, that you can overdo or will not be able to comply with. So the yeast is really a hard constraint. So if you forgot to add yeast into the pandesal, what happens to your finished product? It might look like um, the crust, no, a crust, no, the crust that you use in baking a pizza. Magmumukha siyang pizza crust, no? Hindi siya magmumukhang pandesal kasi hindi mo nilagyan ng leavening agent, no, which is very important. It's a hard constraint in baking a pandesal. Okay. Now, a chance constraint only requires that the original constraint will be satisfied with some very high probability while leaving a small chance that it will be violated a little bit. Okay, so it only says that there are some constraints that you can violate a little bit. So there's a small chance, no? Okay, so let's not be too concerned about that chance constraint. Okay. Now, the goal of optimization, or robust optimization, is to find a solution for the model that is guaranteed to remain feasible and near optimal for all plausible combinations of the actual values for the parameters. There are four basic assumptions in robust optimization with independent parameters. When we say independent parameters, the parameters do not are not related not to each other such that if you change one, you need to change the other one. No, there's no need for that. You can change one parameter and still not affect the other parameters. So the four basic assumptions are each parameter has a range of uncertainty surrounding its value. And this parameter can take any value between minimum and maximum specified by this range of uncertainty. And these values are influenced by the values taken on by the other parameters. And all the functional constraints are in either less than equal or greater than equal form. So it's not applicable to fixed requirement constraint. No, yung equality, it's not applicable to that. Okay, and robust optimization involves assigning a conservative value to each uncertain parameter and then find the optimal solution for the revised problem. For our example, we go back to Windor Company, wherein the production rates at plant 3 are uncertain. Okay, this is about producing doors and windows. And initial estimates were given that 3 hours per door and 2 hours per window could be off by as much as half an hour each. Which means um, producing each door, we cannot be really sure, no, if producing each window would take 3 hours. Maybe okay, and for the window, but we're not that 100% that it will take only 2 hours to produce. That's the meaning of it could be off by as much as half an hour each. Maybe longer than 3 hours, 3.5 hours to produce each door, and maybe 2.5 hours to produce each window. Because the production processes are different for doors and windows, the value of each of these parameters is uninfluenced by each other. So these are independent parameters. So what is the technique here? You have to set the parameters in plant 3 to their conservative values by adding half an hour for the door and half an hour for the window. So, ang gagawin mo, kailangan may pasobra. That's the meaning. We cannot tell our men or workers that we only require 3 hours. That no, I'm sorry. We cannot uh, we cannot put in our on our spreadsheet, no, that the requirement is only 3 hours for the door and 2 hours for the window. We have to have a latitude, sabi nga ng author. We have to have a latitude. We have to have a pasobra. Okay, so we will set the requirement to 3.5 hours for the door and 2.5 hours for the window. And then we will run solver again. Okay. A range of uncertainty may also exist involving other parameters in the model, like objective coefficients and right-hand side. So here in our, going back no, to our example of door and window, wherein we need to have pasobra or latitude, no, by adding half hour each to the left-hand side. Now, we're referring to the left-hand side here, which refer to the hours required to process the windows and doors in Plan 3. So it's we're referring to the left-hand side, the required, okay? Because in the right-hand side, we have the available hours. Okay. So at least, no, you have the idea, no, what robust optimization is really about. It's just having a pasobra, a latitude. So instead of say telling your clients that, let's say, no, I go back to that previous example, no, instead of having only, let's say, um, you will work within a week, you have to have some latitude. So you have to add, no, you have to give yourself an allowance. So you have to add more days, no, because kung masyadong gipit yan, no, magigipit ka, wala kang pasobra. You have no latitude at all. That's the whole point, no, of robust optimization. Now we have here some rules that you should follow. Okay, so for each functional constraint in less than equal form, use the maximum value. For each uncertain coefficient on the left side, and the minimum value for an uncertain right-hand side. So instead of, let's say in the left-hand side, instead of 3, you add, okay, add a little more. So you will set it not to 3, but to 3.5 or 4. No, you have to have some data to find out, no, what is the applicable value. Okay, and then this is for the ano to, resource constraints. No, you have the less than equal form, and in the right hand side you write the minimum value. So instead of, let's say, 10, you can lessen it, no, parang ganito lang yan eh. Instead of telling your men or your workers that you have 12 hours available, you would tell them that you only have 10 hours, so that meron kang pasobra na 2 hours, 'di ba? Hindi mo ginigipit yung sarili mo. Ganun 'yon. Parang ikaw lang, halimbawa, si mami mo, he would ask you, how much do you need? You wouldn't say the exact amount of, let's say, 1,000. You might give yourself some leeway, no, and tell her that you need 1,200, and actually tell her that you just need 1,000, but then you have to have an allowance of 200. It's just the same thing, no? It's very practical, actually. Robust optimization is really very practical. Now, on the other hand, for each functional constraint in greater than equal form, use the minimum value for each uncertain coefficient. And the greater than equal, the maximum is just the opposite, no, of what I have discussed in the preceding bullet. And for an objective function in maximization form, use the minimum value for each uncertain coefficient. And for an objective function in minimization form, use the maximum value for each uncertain coefficient. Now, this is about the objective coefficient. The first two bullets were about functional constraints. And the last two is about the objective coefficient. So these are two different parameters. Then run solver again to the always run solver for the revised model. The resulting solution is guaranteed to be feasible so long as all parameters fall somewhere within the ranges of uncertainty. So that will be all for today.